So yesterday we have discussed the dimension and basis and all these things. Okay, so we have seen that. So K field V vector space K field V vector space. Then we have seen that V has a basis, right? Now we will define dimension V, or maybe the K dimension of V, to be cardinality of a basis of V. Okay. Now the first question should be: is this thing well defined? Is this thing well defined? I mean, by that we mean, is it well defined?
Yes.
That is, we have to show that any two basis of V has okay. So we will do it for the finite case. Over our discussion, mostly the results are developed over the finite dimensional structure. Okay. So suppose beta is a basis of V, V1 to Vn. Okay. And beta prime is another basis of V, which has W1 to Wm. Okay. Now, see, we won't be able to prove everything. So we won't be able to prove everything, elaborately, but we will at least give you the idea. So what is that? So suppose you take W1. Okay. So W1 is a linear combination of these things, right? Right? So see, the right hand side is non-zero, right? So the left hand side has to be non-zero. I mean, the left hand side is non-zero, so the right hand side has to be non-zero. So not all Ci can be zero, right? So without loss of generality, let C1 is non-zero. Okay. Then you make this set V1. I mean, you replace V1. I mean, see, the vector which has a non-zero coefficient in the representation of W1, we are dropping that vector. Okay. Okay. You will be able to show that this is a basis. Okay. I am just giving you the idea. So you will be able to show that this is a basis. Then Similarly, you will be able to draw V2 and all that. So after some process, you will get this. Every vector will be inside this basis. Okay. So by that you get m less than equals to n, right? And similarly, by dropping vectors from beta prime and replacing from beta 1, v1, v2, you will show n less than equals to m. So you will conclude m equals to m. Okay. So any two bases will have same cardinality. So one immediate corollary is that if k dimension of V is n, then any set of n, yes,
বলছো তুমি m is equal to n টা কেন হলো?
কোথায়?
এই যে ফার্স্ট কেসটাতে তুমি বলছো না m টা is equal to n, ওখানটা ঠিক বুঝলাম না।
You will draw V1 first, then V2 for W2, then V3 for W2, W3, and so on. So you will be able to include every vector here in this set, right? So beta m, so beta m will have something like this. It's supposed to have something like this. Right?
আচ্ছা বুঝতে পেরেছি।
And similarly the opposite. So any set of n linearly independent vectors will form a basis. You understand why? You understand why? So suppose you have a basis of alpha 1 to alpha n, okay? And you have this n linearly independent vector, or maybe say this is V1 to Vn as above, okay? And you have here alpha 1 to alpha n, okay? N linearly independent vectors, okay? Hello?
Yes.
This is a basis and these are any linearly independent vectors. So what should we do now?
We will express alpha 1 as a linear combination of v1, v2 over vn, and alpha 1 alpha 1.
Yes. So he is saying that any linearly independent vectors will form a basis. Okay. So these are linearly independent. Okay. So call it S. So if S is not a basis, then what? There exists V belongs to V minus tan S, right? True?
Yes.
Because tan S is a subspace of V, right? Because this S is already linearly independent. So if it's not a basis, it fails to span V, right? So we are taking a V out of span S. Okay? And we have seen last day that this is a linearly independent set, right? If you take a vector out of span S, then this set becomes linearly independent, right? Right?
Yes.
So you continue to do this process. Okay, let's call it W1. So you continue to do this process until it terminates. It will terminate because it is a finite dimensional vector space. Okay. Wait a minute. So W1 is away from this. Okay. I want to show that basically I will have to show that W1 is in span S basically. So what can I do? That vector dropping was available for So by that way, suppose you reach W1 to say Wm. Okay. Now you see the problem. At some point you will be able to such that S prime, such that span S prime is V. Okay. But you see, then this is the basis of V, right? But this is the basis of V as well. But the cardinality don't match. Okay. The cardinality don't match. So the only process is possible if this set is just null set. If W1 to Wm doesn't even exist, that is span S is V. Okay. So I'm just giving you a sketch because I mean otherwise I will have to write too much. In 6 months I will have to cover the syllabus, so it's impossible to go through the theory rigorously. Everything will be done in the M.Math batch or maybe in the Ph.D batch. So this was one. Okay. We have managed to establish the cardinality of the basis, which is the dimension. And okay, so let's compute a few dimensions. So let V belongs to M&R. Okay. Or maybe let's take M and K for any vector space. Okay. This is a vector space, right? This is a vector space. Can anybody tell me what is the dimension of this thing? This is n cross n matrices over K. Can anyone tell me what is the cardinality? I mean, what is the basis of this? I am defining EIJ. What is EIJ? EIJ is a matrix. Yeah.
I equals to 0 1 or I not equals to 0 0.
Yeah. So how should I write it? Maybe I should write it as AKL. Okay. Is a matrix. KL. This K is small k, less than equals to n, such that I equals to 1 if I equals to k, j equals to l. 0 otherwise. Okay. Can you show that this is the basis? I mean, beta is the set of EIJ, where so these are n square elements, right? N square matrices, right? So each matrix looks like this. 1 at the ijth entry, 0 everywhere else, right? 1 at the ijth entry. Can you show me that this is a basis? I give you 2 minutes. Show that this is the basis. Yes. Hello.
Okay, sir.
So this is not a very difficult thing, right? Because why is it echoing all of a sudden? Hello.
আমার echo হচ্ছে।
Hello. Hello. Hello.
হ্যাঁ, ঠিক আছে, ঠিক আছে, হ্যাঁ, এখন ঠিক।
So basically, uh, hello. Hello. Am I audible?
তো ঠিক আছে দাদা, হ্যাঁ ঠিক আছে।
So basically, see, you take any matrix Aij, right? So Aij is the ijth entry of A. So it is nothing but Aij into Eij summation, right? Over I over j. Correct. I mean you take it A11, A12, A21, and A22. So you can write A11 times 1000 plus A12 times 0100 and so on, right? So that's what you are doing. So clearly, this spans M and K. Okay. So that beta, I mean that set spans M and K. And if this is zero, if this is zero, right? Then what do you get? You get a whole matrix C11, C1n up to Cnn, which is a zero matrix, right? Which means every element is zero. So thus it has a, I mean thus this thing is a indeed a basis. So what is the dimension? What is the dimension?
n square.
N square. Okay. Now example 2 or maybe continue with example 1. So how do I write it? Let's write in sim. Sim is a space of all or maybe I should write space of all symmetric matrices, okay, over in MNK such that A equals to A transpose, okay, and let's write SK sim to be all those A belongs to MN or MNK such that A equals to minus A transpose, okay. Can you tell me about the dimension of these two?
ফার্স্ট এটা হবে n into n plus 1 by 2 আর তারপরে একটা হবে হচ্ছে
So
হ্যাঁ
dimension of sim. So first try to
n into n plus 1 by 2 or n into n minus 1 by 2.
হরিনারায়ণ, এই হরি তোর ওই যে অভ্র যে ছেলেটা ফোন করেছিল না, ফোন করেছিল সে ঘুমিয়ে ধরতে পারি, তারপরে যখন কল করলাম তারপরে তাকে পেলাম।
হ্যাঁ আসলে দাদা ওদের পরীক্ষা চলছে তো ওদের ওই 2-3 জন আছে
তাহলে
হয়তো
ওরা
হ্যাঁ নেক্সট মান্থে জয়েন করবে।
সে যখনই করবে সেটা কথা নয়, কিন্তু ইয়ে আর কি, এই এক সেকেন্ড দাঁড়াও তো। Give me a one. Give me a one. Hello. Okay, so this is how it looks like, because AIJ is basically AJI. Okay, so this is how it looks like, right? But see, I can write it like this: A11 1 0 0 0 0 0 everywhere, plus A22 0 1 0 0 0 0 0 everywhere, right? And similarly ANN 0 0 0 0 only one here, right? Plus A12 0 1 1 0 everywhere else, right? Then A13 0 0 1 0 0 1, sorry, 0 everywhere else, right? So how many matrices are there? How many matrices are there?
so n plus n
In the first row there are n, right? This is basically E11, then E22, then ENN, right? So for the diagonal entries you have n many. And for the off diagonal entries, how many off diagonal elements are there? N square minus n, right? For that you are choosing n square minus n by 2, because A11 is equal to A12, right? Sorry, A12 is A21. So it's enough to choose A12. So for AIJ and AJI, you have to choose only one of them. So the dimension is this, okay? Which is just this. Clear? What about dimension of SQ sim?
না ওটা n into n minus 1 by 2 হবে।
So for skew symmetric matrix we have AIJ is minus AJI. So the matrix will look like 0 0 0 0, A12 minus A12, A1n minus A1n, and so on, right? So basically you can write it like A12 0 1 minus 1 0 0 0. These are all linearly independent matrices, you can check. and similarly, I mean for Aij dot Aij, you will have one here and one here, where this is the ijth place and this is -1. This is the jith place. Okay. So that is your basis. Okay. So you see again, just a minute. So you see again, you have n square minus n non-zero elements at most. That is n square minus n. You are choosing only a12 because automatically a21 is minus of that. So the dimension is this. Okay. Yes.
বলছি যে তুমি সিমেট্রিক ম্যাট্রিক্সের জন্য যে তুমি ডায়াগোনাল এলিমেন্টগুলোকে জিরো করলে, কিন্তু ওখানে ফিল্ডটা যদি তোমার এমন হতো যে মানে দুটো এলিমেন্টকে যোগ করে যদি জিরো না হয়, তাহলে তোমার ক্যারেক্টারিস্টিক্স অফ দ্য ফিল্ড যদি মানে টু যদি না হতো, তাহলে তো তোমার ডায়াগোনাল এলিমেন্ট জিরো নাও আসতে পারে।
Sorry. What is your question, Bhai?
আমি বলছি যে তুমি
So he is basically taking what if we take. So he is saying that aii is equal to minus aii, right? By that we mean 2 aii is 0. So he is saying what if the field is, it's a good question. What if the field, that's a good question. The field K is z mod 2z, right? Because that's the only time where 2 equals 0. Because aii is non-zero, of course. We are assuming aii to be non-zero. Implies 2 is congruent to 0 if aii is non-zero, right? So over z mod 2z, you will have, actually you can compute it by hand. So you see, I mean, what will you get? The skew symmetric matrix, you can put 1 here. So one matrix will be this, like the off diagonal will be this, and the main diagonal will be 1 equals to -1, right? Because 1 and -1 are equal. So this is the only skew symmetric matrix, right? Right. You understand? Over z mod 2z, maybe I am taking it to be 2 cross 2. That's one thing. So I am taking it to be 2 cross 2. I mean 2 cross. What about? So one is this option. No, the problem is that there is no, I mean, the notion of symmetric and skew symmetric makes no sense in over, I mean, because this is again equals to this. You understand?
No, দাদা স্কিউ সিমেট্রিক ম্যাট্রিক্স হতে গেলে তো ডায়াগোনাল এলিমেন্টগুলো 0 0 হতে হবে।
No. Why? That is because aii equals to minus aii and 2 of aii is 0, which implies since 2 not equal to 0, then we can say aii is 0. But what he is saying is that if 2 and 0 are equal, then what? So that's the only case when z mod 2z, right? But what I am trying to say is that, see, the notion of symmetric and skew symmetric, I mean the notion of symmetric and skew symmetric matrices does not make sense over z mod 2z. Why? Because you see, so aij is 1 or 0, right? Now, so if you take aij equals to minus aji, so suppose aij not equal to 0, that implies aij is 1. Automatically you have no other choice. So if aij equals to minus aij, you get 1 equals to -1, right? That is always true. And also aij equals to aij, I mean, so 1 and -1 are equal. So always aij equals to minus aji and always aij equals to aji. Understood?
হ্যাঁ, মানে স্কিউ আর সিমেট্রিকের মধ্যে কোনো তফাৎ রইল না।
it doesn't make any sense to talk about symmetric and skew symmetric over Z2.
Exactly.
Okay. So now I will request you to observe this thing, that n square n into n minus 1 by 2 plus n into n plus 1 by 2. This is n square, right? Right? And also, so this is SK sim and this is skew sim. Sorry, this is only sim. And what is the intersection, by the way? What is it? I mean, what is A when A is both symmetric?
Zero matrix.
Right.
Trivial matrix.
And skew symmetric. So you see that this is basically singleton 0, isn't it? So these are two subspaces which have no intersection, right? Now let's talk about, suppose W1 and W2 be two subspaces of V. You know what W1 and W2, I mean W1 plus W2 is, right? It is like W1 plus W2, the set of all vectors, such that Wi belongs to capital Wi, right? And this is a subspace of V. And you will be able to see that this is a subspace which is the smallest subspace containing both W1 and W2, and W1 intersection W2 is the largest subspace contained in both W1, W2. And this is what W1 plus W2 is, the smallest subspace containing W1 and W2. Okay. So this is how you look at the W1 plus W2. Okay. So when we say, what does this notation mean? What does this notation mean? So we say W1 plus W2 or maybe we denote W1 plus W2 by W1 direction W2 if W1 intersection W2 is 0. Okay? Okay? Now you see what is SK plus what is SK sim plus sim. This is a subspace of M and K, right? Okay, there is another thing I need to tell you. Do you know what is the dimension of this thing? Okay, this is a standard result. Dimension of W1 plus W2 is dimension W1 plus dimension W2 minus dimension W1 intersection W2. So in this case, the dimension, in this case, dimension W1 direction W2 is basically dimension of W1 plus dimension of W2. Okay? Because the intersection is 0. So we have already seen that this is the direction, right? So this sum can be taken to be this, right? And dimension of this side, I mean dimension of this is n square into n minus 1 by 2. dimension of this is n into n plus 1 by 2. You add them up, you get dimension of SK sim, direction sim is basically n square, right? So you have a subspace of MNK which has the same dimension of MNK. So what does it mean? It means SK sim direct sum sim is basically the whole MNK. Okay? Understood? In other words, so any element in the RHS is also an element in the LHS. So in other words, for any A belongs to MNK, there exists B belongs to SK sim, C belongs to sim, such that A is B plus C, right? That's true, na? Right? Is that clear? Okay. Can you tell me what is this B and C? This is class 12 level. Can you tell me what is this B and C?
Okay, A plus A transpose by 2.
A plus A transpose by 2 plus A minus A transpose divided by 2.
Okay. Yeah, so what is the date today? Is it 18?
18.
হ্যাঁ দাদা
Okay. So they are saying is that you can write A to B half. Okay, let me write it like C plus B. C plus B. A into A transpose half A minus A transpose. Okay. So every matrix is decomposable into two parts, and we have seen that this decomposition is unique, right? This direct sum decomposition is unique. Okay. So now let's take this example 3. This is not a finite dimensional vector space. Okay. So I am taking CR. What is that? Set of all functions. Maybe the notation is a little bit misleading. From R to R. Okay. This is a vector space over R. Over R. You understand the operation? So by defining suppose F plus G. Okay. So how is F plus G defined? So F plus G of X is just Fx plus Gx. Okay. That's the addition. And if C is any scalar, Cf of X is just defined to be C times Fx. Okay. Okay. Can you find W1, W2 subspace of FR such that FR is W1 direct sum W2? I give you 2 minutes.
হ্যালো দাদা, বলবো? হ্যালো।
So, are you able to come up with something?
Sum of even function and odd function.
Yes. Who is this, by the way? কে বলছে সেটা বললে আমি নাম এখনো বলা চিনতে পারি না সবার, মানে যাদের যারা নতুন হচ্ছে চিনতে পারি না।
আমি
আচ্ছা, এই ঋতিক তোর বলা চেঞ্জ হয়ে গেল কি করে?
আরে না, গলাটা ধরে গেছে।
ওকে, so any function we know that it can be written as right. So this is the odd part, this is the even part, and you know a function can never be even and odd at the same time unless it is a zero function. So are you getting some similarities between these two decompositions? You see, they are exactly the same thing, right? They are the exact same thing. Okay. So remark, even K is a special set of functions from K to the power n to K to the power n. Okay. The linear transformation. We will see that later. Okay, let me see what else I need to go through. What else? What else we need to go through? Just a minute. Let me check. I have written it down somewhere. Just a minute. Symmetry given not pretty much okay. There was something I needed to go through. Where is the document? There is something called basis change. Okay. Just a minute. Let me open the book. Okay. So this is the section we are going to. So suppose V is an n-dimensional vector space, and these are two bases of V. Okay. So see, we have seen two bases, they have same cardinality, everything is fine. But we are trying to establish some, what should I say, some correspondence. I mean, how to go from one basis to other. Like a coordinate change we used to do, like coordinate rotation we used to do, something like that. So you are writing alpha j prime in terms of beta. Okay. So Pi are the matrices. Understood? Now x1 prime to xn prime be the coordinates of a given vector alpha in the ordered basis of beta prime. Do you understand what we mean by coordinate? So see, in Rn you see that suppose there are point like this, there is a point like this, and you say C1 to Cn is the coordinates of the point, say A. Okay. So why are these called coordinates? And you will say this is the first coordinate, this is the second coordinate, this is the nth coordinate. So basically what you are doing is that you are using this basis. Okay. So a coordinate is nothing but, I mean, an array of coefficients that represents a certain vector with respect to a certain basis. Good. So when we are writing A equals to C1 to Cn, we have that basis a priori, which is 1 0 0 0 0 1 0 0 0 0 1. Okay. So we are extending that concept when we write x1 prime to xn prime be coordinates of the given vector alpha in the ordered basis beta prime, that is alpha is this. Okay. And I think with respect to beta, some coordinates are given earlier. No, it's not. Okay, no, it is here. 1-to-1 correspondence and beta. No. Okay, let's see. So this is the basis. Let's see what's there doing. Okay. So now they are putting the values of alpha j prime, that is this, taking the sum outside and doing this, they get this. Okay. So you get, I mean, so xi prime was, xi primes were coefficients or coordinates with respect to beta prime. By that they are trying to obtain coefficients or coordinates with respect to beta, and this is the coefficients. Okay. So if you write summation xi alpha equals to, your xi is this, summation Pij what j. Okay. Now you see P is an introscene matrix, okay, where Pij is the ijth entry of P. Okay. So x prime, x and x prime. So basically by x they are writing this, and by x prime they are writing this. Okay. So by this relation, this is clear to you. Okay. Okay. Now what is x? X is nothing but the representation of alpha with respect to beta, and x prime is nothing but the representation of alpha with respect to beta prime. Okay. So that is the relation between two different bases, and P is said to be the basis change matrix. Okay. You go through the theorem. Okay. Summarize as follows. Okay. Just read the statement. Just read the statement. That's it. Okay. So that was our gist of the the discussion earlier. Suppose P is an n-crossing matrix over F, and B is an n-dimensional vector space over F. Okay. Now you see, what did we establish in the last time? Okay. We established that given two bases, there is a matrix, right? But given one basis and one matrix, can we associate another matrix? Another basis. Can we do that? The question is clear. So, for two bases, we have a basis change matrix. But given an invertible matrix, does it? Is any invertible matrix can be thought of a basis change matrix? That should be the very natural question. And you see, there is the answer. Okay. So I give you 2 minutes to go through this. Okay. See what they have done. See, I can write everything down, but that will take a whole lot of time. The pace I am going to, you understand, I have only say 25 classes to complete the whole linear algebra course. So there is no other way to, skip my way through the syllabus.
দাদা বলছি পুরো বইটাই কি আছে?
Yes. Hello.
বলছি পুরো বইটাই কি আছে সিলেবাসে?
না syllabus কি আছে? Give me a minute. Vector space is there, linear transformation, elementary canonical forms, rational Jordan forms. Not the whole rational Jordan form. Okay, half of this chapter. Then inner product spaces. Okay, so it's like 2, 3, 6, half of 7 and 8.
না বলছি ওই ডিকম্পোজিশন থিওরেম ওগুলো নেই না, এই সাইক্লিক ডিকম্পোজিশন থিওরেম বা
Those are
আহ,
in chapter 6 and 7. Our main majority of our time and focus will go there. That's the reason we are, doing everything in a hurry. Okay.
ঠিক আছে।
So linear transformation, chapter 6, and yeah, those chapters will take a little bit more time. There are other very important things also. Operators on linear product spaces, bilinear forms, but these we will cover, I think, in the PhD class. These are not needed in the in this in this course actually. In this module 2 course, these are not needed. Okay, so please go through the theorem 8. You can see this in detail at home. Okay, just look at the statement and just have a look at the sketch. Don't go into too much detail. Okay, there is another very standard question. This just came to my mind. So suppose you take k equals to z mod pz. Okay. So what is the dimension of Mn k? Not exactly Mn k. I should write what is the dimension of gln k. Set of all set of all what? Set of all invertible matrices. Not exactly. Number of invertible matrices. That is the question, I think. Matrices over. Okay. So what is the number of invertible encross in matrices over K? You know how to do it.
না দাদা একটা অ্যাপ্রোচ মানে বলেছিল
What?
মানে ধরো এই যে তোমার একটা ম্যাট্রিক্স নিচ্ছি, ঠিক আছে, এন ক্রসের ম্যাট্রিক্স নিচ্ছি। এবার ইনভার্টেবল মানে কি, ওর র্যাঙ্কটা পুরোটাই হবে, মানে কি বলবো, এন ক্রস এন ম্যাট্রিক্সের র্যাঙ্কটা এন হবে।
So his first thing he is saying that A is invertible if and only A, rank A is n. So everyone knows, everyone here knows the definition of rank of A. Okay.
তাহলে র্যাঙ্ক যদি এন হয় তার মানে ওটা মানে কি, এন খানা লিনিয়ারলি ইন্ডিপেন্ডেন্ট রো হবে।
So this is if and only if A has n linearly independent rows. Yes.
এবার আমি একটা আরবিটারি একটা এ ম্যাট্রিক্স বলছি, যেখানে আমি মানে এটা আমি দেখবো কিরকম দেখতে হচ্ছে।
Yes.
তো আমি ফার্স্ট রোটা আমি যাই করি না কেন, সেকেন্ড রোটাও স্কেলার মাল্টিপল হবে না।
So he is saying that the first row, so row 1, so row 1 you choose in any way, just a nominal row. So how is that possible? This is p to the power n minus 1, right?
হ্যাঁ হ্যাঁ
P to the power n ways you can fill up the first row, just minus the null row. Okay. The second row, the row 2, it should not be the multiple of the first one. Okay. So whatever, so how many multiples of first row are there? So you can multiply the first row by 0, you can multiply the first row by 1 or 2 or up to p minus 1. So if you have a fixed first row, row 2 cannot be lambda times row 1, where lambda belongs to the scalars. These are only scalars in Z mod PZ. Okay. So row 2 has option p to the power n minus p. Okay. Now row 3 cannot be lambda times row 1 plus mu times row 2, right? Row 2 cannot be the linear combination of those two. Each of row has to be linearly independent. So this lambda and mu belongs to what? Again 0, 1, 2, p minus 1. So row 3 have options p to the power n minus p square. Okay. So this way it will be p to the power n minus 1, p to the power p to the power 0, p to the power n minus, this is a small p, n minus p up to p to the power n minus p to the power n Okay, that is the answer. Another thing I need to say. So we know that for any set or any set, if you have S1 union S2 union S3 is basically the cardinality is basically S1 plus S2 plus S3 plus S1 right. This is the formula. But what happens if you take this, where Wi are subspaces of V? Okay. Wi are subspaces of V. What can you tell about the dimension? You see, S1 union S2 cardinality is what? Cardinality S1 plus cardinality S2 minus cardinality S1 intersection S2. So it is at par with the dimension of W1 plus W2, right? We have shown that W1 plus W2, this is the dimension W1 plus dimension W2 plus dimension W1 intersection W2. Okay. So these two are at par. But is it true that this is equal to summation Wi minus summation dimension Wi intersection Wj plus summation dimension Wi? I mean W1 intersection W2 intersection W3. Is it true? Is the relation true? So it is actually not true. You take V equals to R2, you take W1 generated by 1, 0, that is the x-axis, W2 generated by 0, 1, that is the y-axis, W3 generated by 1, 1, okay, that is the diagonal. Now you see, dimension of Wi is 1, okay, for all I 1, 2, 3, and W dimension, and sort of you see that Wi intersection Wj is always the origin, right? So dimension Wi intersection Wj is always 0. So you come here, dimension of W1, I mean W1 plus W2 plus W3 becomes R2. Okay. So dimension here becomes 3. I mean sorry. So this is R2. So the dimension becomes 2. And here it is 1 plus 1 plus 1 3. But every term here is 0. Okay. So this is not equal. Okay, we will conclude today's class here. I request you guys to look for problems. Okay.
দাদা
Yeah.
একটা কোশ্চেন ছিল, ওই যে তুমি ওখানে বললে না কতগুলো ইনভার্টেবল ম্যাট্রিক্স থাকে ওপরের প্রবলেম। এবার আমি একটা মানে জিনিস ভেবেছি, সেটা হচ্ছে তোমার এমন কতগুলো ম্যাট্রিক্স থাকবে যাদের ডিটারমিনেন্টটা 2 বা যে কোনো একটা ফিল্ডের নাম্বার, এইগুলো কিভাবে বের করবো, কোনো টেকনিক আছে?
How many matrices are there with?
With the determinant I mean some number which belongs to the field. I mean suppose how many singular matrices are there, or how many matrices is
Singular
determined?
matrices is very easy. You just do, I mean singular matrices is very easy.
হ্যাঁ ওইটা তো হয়ে যাচ্ছে, ওইটা ঠিক আছে, কিন্তু ধরো কোনো একটা আর্বিট্রারি নাম্বার
I
নেই।
mean the total number of members in that set, that is you see p to the power n, p to the power n, and all that, and just it's like for n square element given p option. I mean, so p to the power n square minus this thing is singular. Now, I mean, how many matrices have determinant 1, determinant 2? That is your question, right?
Yes, yes, yes.
So I am thinking, are these equally likely? I mean, is every element, I mean, is every value equally likely to appear? I mean, can I just divide by p? Or maybe p
No,
minus
not
1? Actually, there was a trick. I mean, I used to do these things actually.
দাদা ওই সিঙ্গুলারটা তুমি এটা আমি যেটা বললাম ওটা কি করে এসছে, ওটা ওই সম্ভবত ফার্স্ট আইসোমরফিজম থিওরেম যে গ্রুপ থিওরি ছিল না, ওই এমন একটা ম্যাপিং ধরা হতো যাতে করে কি ওই কার্নেলটা তোমার এই সিঙ্গুলার, সেটা পর সিঙ্গুলার ম্যাট্রিক্স হয়ে যায়। তারপরে ফার্স্ট আইসোমরফিজম থিওরেম অ্যাপ্লাই করে ওখান থেকে করা যায় আর কি। কিন্তু এবং সব হোমোমরফিজমের তো ধরো কার্নেলটা ওরকম আসবে না, মানে ওই
No, no, no,
ডিটারমিনেন্টটা
no.
তুমি
Why do you need to do that? Just these are all matrices which are non-singular,
হ্যাঁ
right? You minus subtract it from p to the power n square, which is the total number of matrices. That's it. What is the total number of matrices in this M n k? M n p z mod p z. In square elements, p options for each of them, so that is p to the power n square. Done.
হ্যাঁ ঠিক আছে হ্যাঁ
Okay, for each, there I have to think. Let me think, but I think this can be done. I think this can be done. I mean, the way you said it, like using the group homomorphism, this is a good problem. Please send it in the group. Okay. I mean, what about, how about if we define the determinant map from Mn z mod pz to z mod pz? Okay. How about this? So if this is a group homomorphism, okay. But will it be a group homomorphism? Determinant A plus B, will it be determinant A plus determinant B? No chance. No chance. Okay. But determinant AB is determinant A times determinant B, right?
হ্যাঁ
So this might be okay. So I mean, see, GLN, I mean the set of all invertible matrix GLN K, this is a group under multiplication, right?
yes
Group under multiplication. So now I mean determinant AB, this is determinant A into determinant B.
হ্যাঁ
Okay. So now this is, I think, now this is true, I think, because what I said, these are equally likely. I think this will appear because I mean, so for one, this is of course a surjective map. This is of course a surjective map. Yeah, I mean, this is a surjective map. Is it clear that this is a surjective map? You take this matrix
হ্যাঁ এটা অবশ্যই সাবজেক্ট দিতে হবে।
A1, 1, 1, 1. Okay. You change A once you make it 1, then 2, then 3. Okay. And determinant of this thing is just A. So you can make it surjective. Just a minute. Yes. Okay. So this is a good problem. Okay, let's put it as a homework. So you understand the question?
হ্যালো দাদা, দেখো জিএলএনআর বা এসএলএনআরটা তো আস্তার সঙ্গে আইসোমরফিক হয়, ঠিক আছে? এবার আমার
those are in R. Those are in R. In fact, I will have to check this property as well. I mean, is it?
না জিএলএনআর বা এসএলএনআর তো আস্তার সঙ্গে আইসোমরফিক।
Those are in R. Those are real matrices.
হ্যাঁ।
These are not real matrices.
ও আচ্ছা আচ্ছা, যে তুমি ইয়ে ধরেছো আজকে। ও সরি সরি সরি।
So I mean we will have to check these things, okay? We will have to check this relation. I mean it holds in R, but does it hold in Z mod PZ? And another thing what he was saying is that GLN Z mod PZ, or maybe for any K field, GLN K mod SLN K, I mean is it isomorphic to K star, that is K minus 0? So those things we will have to check out. I think it will be true, because I mean what is the kernel of this homomorphism, right? What is the kernel? Or maybe I mean this is not here, I mean this is going to Z mod PZ star, right? Sorry, the units only. So what is kernel determinant? I mean which are the matrices that maps to 1? Determinant of 1, right? So that is SLN PZ. So he is right in that case. Yes, Nikhil, you are right. Matrices of determinant 1, right? Hello, Nikhil? Right, you are. Right, you are. So see, I mean then it is done actually. You understand? Because then I mean every element in Z mod PZ star, okay, they correspond to some coset. I mean correspond to some coset in, I mean in what should I say, in GLN. My handwriting is going just, what should I say, right? This corresponds to some coset under this isomorphism, and every coset has the cardinality of SLN Z, right?
হ্যাঁ একদম।
That is from Lagrange's theorem. Like
হ্যাঁ
in G mod H, every coset has a cardinality of H. So that is true. So basically, the cardinality of SLN Z mod PZ, what is that? From here, that is cardinality of GLN Z mod PZ. These are G. This is G. I know. This is by So what I said in the first attempt was correct. Okay, so I will have to conclude today. Ritik, thanks for this good problem. This was a good problem. Chalo, tata.